All right, so let's start right away. So where were we? You might remember that I told you last time that one of the use cases of XML over JSON is by the publishing industry, where you have documents that are actually scientific papers, books, and so on, where you use the elements to annotate, just like in LaTeX, for example, you annotate parts of the documents. In XML schema, you can say so with mixed equals true. That basically says that's a complex type that has an element B that is a string, so that would be this, right? But in order to say that it's okay to have text around it, so you basically say mixed true, and that allows you. So that basically says that you can annotate with B portions of text, and you can even do it as many times as you want because max occurs is unbounded, right? So this is how you control this text-oriented or publication-oriented XML. And that is one of the strengths where XML really shines. Okay, what else do we have? Attributes. How do you validate attributes? Well, you might be happy to learn that the types of the attributes, that's the same as the types of the elements, the atomic types, of course, because you cannot have complex types in attributes. So the way you do it is you define, here I put the whole schema, an element person. That is a complex type with a sequence of last and first that are strings. So that's what you see here. How can I add this birth attribute? Well, just after the sequence, I have this, again, it's static attributes, the name of which is birth and the type is date, because date is in this huge list of atomic types at your disposal, right? So this is it. So the type for attributes and elements that just have text inside is the same, works in the same way with this type, right? We call them simple content when there's just text inside, right? This we call mixed content, and this we call complex content, right? So complex content, mixed content, and simple content here, okay? All right. So now what I did is that, just like I did for JSON, I took the great language game, converted it to XML. So that's what you get when you convert it to XML. It's one way of doing it, right? So this would be guess, target, country, the choices, you know, with this way of using the plural form here and the singular for the repeated elements to basically have an array of strings. So this is what I get. Now it's getting back to a question you have. Should I use an attribute or should I use an element, right? For example, guess, target, you could also use attributes. What I'm giving to you here is a taste of what people do in practice. So somehow the sample here kinds of is some sort of ID in there, right? So this feels like you put it as an attribute in there because it's kind of a bit special, kind of the meta data of this game, and the others I just put them as elements. But there is no right or wrong. I could have put these as attributes. I could have put this one as element. That's fine too. But once I have made this decision, I can just define my schema in this way. You see, games, which is a sequence of elements called game in the singular. You can repeat game, right, as many times as you want, unbounded. Game is a complex type with the sequence guess, target, country, which are strings. Choices, which is a complex type itself. You see it nests here. A complex type, a sequence of choice unbounded of type string. So you can have here. Sorry, not unbounded. I put unbounded. I could have put 4 in there, right? Because in that case, it's just 4. So I could have put max occurs 4. That would have worked too here. And then the element date here, which you see uses the excess date. And then my attribute after the sequence, sample, which is of type hex binary. I'm using yet another type, hex binary, that basically has, it's a very good textbook example. This is a lexical value, right? If you write 4, 8, F, 9C, that's a lexical value. It's basically a hexadecimal sequence. But once you validate it against hex binary, in memory, you're not going to have this anymore. In memory, you're going to have a sequence of bits or a sequence of bytes, right? Once you have parsed this. So this is the sort of things that you do with annotation, right? Okay, so you understand the difference, lexical value, typed value? Who does? All right, very good, most of you. Very good. Okay, this is absolutely fundamental to schema validation in general. Okay, and here I'm a geek. I love these things. You might have wondered when I showed you that JSON schema is JSON, XML schema XML, is there a schema that validates schemas? And the answer is absolutely yes. And this here, it exists, it's somewhere on the internet. This is a schema that validates the schemas. it also means it validates itself. So this is the instant and the schema. Yeah, you can look at it. It's basically it's a curiosity, right? It validates itself. You can do the same thing for JSON schema, JSON. So define a schema that validates the schemas, right? Okay, but again, that's just a curiosity. I had to show that for completeness because it's cool. All right, which brings me to data frames. So you see, I wasn't too long on XML schema. It's not much more complex than that, but I just wanted you to see the sort of things you can do with it and how you can add constraints to your documents. Data frames. Who heard of data frames? Wow, a lot of you. Who heard of data frames through Pandas? Oh, wow. Oh, okay. Awesome. Who heard of it through Spark? Some of you, less. Okay. So now, if you already know data frames from Pandas, then today, you are going to get a different formal approach to data frame, but you will realize it's the same thing. Because I'm going to explain data frames in a completely different way. In fact, I'm going to explain data frames as a collection of valid JSON documents under specific conditions. So let me explain what I mean with this. So on the left here, you have a JSON schema that has 3 keys in there: integer, string, Boolean. Remember, and now maybe the puzzle starts adding up, this is closed, meaning that by default in JSON, you don't allow extra properties. So you know there will not be anything else than that, but they might be optional. So this is a JSON schema. Imagine that now I have data and I have 4 documents like this. These are records in there. And ID here is an integer, name is a string, living is a Boolean. So now my question to you, just to see if the pieces of the puzzle add up. If I give you the data frame representation on the right, turns out to be a table, could you reconstruct the 4 JSON documents that are valid against the schema on the left and that would map to the table on the right? Who would be able to do that? Who would not be able to do that? I don't see any raise hand. Who doesn't know if they would be able to do that? Who doesn't know if they would be able to do that? Okay, so let's do it, right? So let's take the first one. 1, Einstein, false. So that would be a JSON object with ID colon 1, name colon Einstein, living colon false, right? Who sees it now? Okay, so what I'm saying here is something really fundamental. If we have a sequence of JSON documents that I might have in some text file, right? JSON lines, for example, and these documents are successfully validated and annotated against that schema that you see right here, then I can actually build a structure like this and look at that same data from a tabular perspective. Who sees it now? Okay, so this is why I'm saying that's a specific kind of data frame. You can see a data frame as a sequence of JSON objects, 4 of them here, that are valid against a schema. And so this is why the intuition behind JSON is that it gives you a way to specify the schema of the data frame itself. This is why we made it close by default. Because in a data frame, you don't have any extra columns. So if we had made it open, allowing for extra properties, we would no longer be able to map it to the data frame. Do you see it? I can't remember who asked that question, but this is the reason why we made it closed by default. Okay, here's another example, more complicated because that is boring. It's a relational table. You've already seen that in your bachelor. But the whole point of big data is that we break these rules, right? So what if now name is a nested array of strings, an array of strings? You can also map this to a data frame. In fact, it would look like what you have on the right. You see, it basically the way you see it's a data frame, but it's not a table. Basically, it's not in the first normal form, is you have lines that don't go all the way through, right? You see that here, in that column, you have multiple values in there, multiple values in there. This is my array of strings here. Who here sees what JSON documents valid against that schema would lead to that record? Who sees it? Wonderful. So ID, comma 1, comma name, comma open square bracket Albert, comma Einstein, close square brackets, comma living colon false close object, right? And you can do the same here. It's an array of just one string, an array of two strings, and so on. Okay, so you see now how the schemas map to data frame schemas, and you can do this. Here's another example. Now I have nested objects, a nested object. So I basically would do it as a visualization by splitting my column headers. I have name, and below that I have first and last, and now I have name.first and name.last here. Who sees the 4 JSON documents here, valid against the schema that give me that? Many of you, wonderful, right? So you have ID1, name colon object, first colon Albert, last colon Einstein, close object, leaving colon false, right? And you can do the same for the others. This is again a data frame with a nested object, right? Now you see the nested object in the headers, that you have a line that doesn't go all the way through, but in the headers. More complicated, what about a fully nested table, meaning an array of objects? So here I have who is an array of objects with name and type, and I can very nicely draw that in my data frame with who, name, and type. Plus, I also have here these nested sequences. Now it's more complicated. Who can rebuild the JSON object that would lead to that record? You can do it. Awesome. Let me tell you how, just for everybody else. You basically have ID colon 1, who colon square brackets, open an object, name Albert, type first, close object, comma, open another object, name Albert, type last, close object, close array, leaving false. I don't know why I thought before saying that, but yes, leaving false. So this is it. That's more complicated. So you see, I can map all of these to data frames. And in fact, I can do that very often. There's just a few constraints. For example, I'm not allowed to use item. I have to specify all of the type. If I put item, I can no longer map this to a data frame. I'm not allowed to open the objects. I'm not allowed to say, for example, additional properties is true or closed is false. So it has to be closed. So there's a few constraints like that, but basically they map very well to each other, right? Just so you see that impedance mismatch, there's this other way that maps to the same visual. Who sees that it also maps to that visual? Now I have an object that has name that is an array of string, type that is an array of strings. Who sees that it maps to the same visual? Wonderful. Okay, so of course the JSON objects would look differently. In fact, that is something you see in practice. We did it with CERN data. I think at some point the CERN data was looking like this, like that was the collisions of all the particles that were stored like this. And we converted it to this because that is easier to understand from a data modeling perspective. So this is the sort of things you do see in practice, this duality between these two representations. Okay. Yeah, that's it. So who agrees now? Data frames are collections of valid JSON objects. Okay, wonderful. That's what I wanted to show you. Why am I saying that? Because once you have a data frames, there are more efficient ways to store it than JSON, which brings me to Parquet and other syntaxes, because there's other syntaxes out there. And in fact, one of the automatic things that I would like you to think of, if you downloaded a JSON dataset from the internet that has a schema that looks like this, and that can be converted to a data frame, meaning your entire collection with billions of objects can be converted to a data frame, and you want to query it, the first thing you should do is validate it, annotate it, convert it to Parquet or a format like that. Why? Because the space on disk is much smaller than the JSON size. So just because it was JSON doesn't mean you should keep it as JSON, right? And Parquet, we'll come back to that. It's much more efficient because you have less to read from disk. Plus, there's many optimizations you can do with that sort of format. If you read the Dremel paper, that's directly related to this, right? Dremel gives you a way of efficiently storing these things in binary form. Okay, which brings me to the formats. So basically, we are looking at lists of maps, right? What is a collection of objects? It's a list of maps. So basically, you can make a few high-level distinctions when you do that sort of things. For example, you have cases in which your data set is flat. It's in the first normal form. right? You don't have any nested data, as opposed to nested data sets where you have these weird vertical lines that don't go all the way, which is a sign that you have a data frame that's not a table. So who sees that tables are a very particular type of data frame when it's in first normal form? Very good. So flat, nested, right? Take a mental snapshot of the two. This is a distinction. In some cases, it's all flat. Things are magically faster when that happens, and sometimes it's nested. Now, this is what the JSON would look like. So what I would want you to see when you look at that kind of JSON, if you look at the JSON on the left, you should automatically see that it's flat, right? And if you look at the JSON on the right, you should see that it's nested. Who sees that? Right. Very good. So there's no nestedness in the one on the left. Second distinction, homogeneous, heterogeneous. Homogeneous on the left means that it's all the same columns and attributes everywhere, and they have the same types, domain integrity, relational integrity. On the right, it's heterogeneous because you have missing values in here, and you might have an extra property in there that wasn't in there, but that is not captured by data frames. Data frames do not do that, right? They do not allow for extra properties. However, there is a recent feature that was added to some data frames. Snowflake did it. Now, I don't know if you saw the announcement of Spark 4, but they also now support heterogeneity with the variant type. Because if you make a column variant, you are in fact making it heterogeneous, meaning that you allow different types. So you see, the heterogeneity is starting to make its way even into data frames. I didn't check if Pandas has variant. Does Pandas have variants? Anybody knows? We'll check. Would be an interesting thing to check. I'm sure one day they'll do it when there is demands. All right, and now this is the JSON. Who sees that the JSON on the top is homogeneous and the one at the bottom is heterogeneous? Very good. Okay. And finally, you can mix that. So I have something on the left that's flat and homogeneous, also known as a relational table in the first normal form, fulfills the three constraints. And on the right, you have something that breaks all of the rules that it can break, right? It's nested, it's heterogeneous, it has extra or missing attributes, it has arrays that are filled with different values, different types of values, and so on. In fact, on the right, you wouldn't even bother put a schema in there, right? It's just your data living its own life without a schema. That's totally fine in NoSQL to do that. You don't have to have a schema. But the price to pay is, if you don't have a schema, things will be a bit slower, right? If you have a schema, then you make things faster because then you can use Parquet or that kind of formats. Okay, so now this is an example. Who sees that it's flat and homogeneous on the left and nested heterogeneous on the right? Very good. I really want you to see that spontaneously. Now, this is JSON. You can do the same in XML, works exactly in the same way. And in fact, you have an enormous list of formats, validation languages, and so on. CSV, well, that's for flat things. YAML, I mentioned it a couple of weeks ago. Data frames in Pandas, Spark, and so on. libxvm for machine learning. Parquet works like magic to compress your valid JSON that looks like a data frame. Protocol buffers, who heard of them? Comes from Google. Protobufs also works in the same way. Avro, and so on, and so on, and so on. You can classify them on the high level. Some of them support nestedness, some others don't. Some are a text format like XML, CSV, JSON. Some are binary like Parquet, protocol buffers. Some require a schema. Some do not require a schema, right? So this is it. And the good news I have for you is that I'm not even going to teach you the others. Why? Because with everything I taught you, now it's a walk in the park. You can go look at them, read the documentation, you will see you already have all the concepts to understand them, right? What I taught you is really generic. All right, so you just need to understand when you discover a new one, ask yourself these three questions. That is one of the starting points. Here's an example. That's not part of the material, I just want you to see it. Imagine you want to learn Parquet, right? You want to see the documentation and so on. So you're going to find in the documentation a list of atomic types. And here, hopefully, you're going to have an aha moment because that list of atomic types is familiar. Boolean, int32, int64, double, decimal, UTF-8, enum, a bit out of the ordinary, binary. This is familiar, right? It has different names, but it's the same thing. It's like going to Wallis and hearing Wallis or Dutch, but in fact, it's the same, almost the same language, right? So what I want you to see is that you already know that. You just need to read the documentation, but that's it. You're already equipped with the knowledge. What about the structured types? It's just called differently. Arrays are called lists and objects are called maps. Some of them also have a record type, and the record just means that you can have keys that are not strings, right? This is another way of doing that. Okay, that's protocol buffers. You also know all these things already. That's like a schema. Last name is a string, first name is a string, title, that's a recursive structure. And you see this required, repeated, optional, works like the min occurs, max occurs in XML schema. Who understands that schema? Right? And I didn't even teach it to you. I don't even need to teach it to you, right? Because that looks exactly like any other schemas we've seen. Just look up the documentation and you will see it will be very easy to understand. So you can basically, with protobufs, define a schema like this, and you can plug it into C++, into Python, into any languages, and you can basically instantiate classes and then write your data to some binary format and read it back into your programming language, right? That is just yet another schema validation technology that is binary instead of textual. All right, I think that's the last slide. So I want to conclude by basically saying that by default in SQL, in NoSQL, you don't have any schema. It's heterogeneous. You might do it in textual format, JSON, XML, and so on. The moment you see a structure and you validate it, if your schema is constrained enough, you basically get a data frame, then it's homogeneous again, and then you get high performance, low memory footprints, and so on and so on. But the beauty of big data and NoSQL is that you can go from the one to the other dynamically on the fly, right? So it's not like SQL where you only have in SQL the right hand side, but not the left hand side, right? And so many technologies like MongoDB give you the choice. In MongoDB, you can create a collection of objects. We'll study it in a couple of weeks. You don't need a schema. But if you want a schema, you can have a schema, and then it will enforce the schema in the collection. You can also create a schema later. You first put the data in the collection, then build the schema, and then validate it. JSON schema, for example, and that's it, right? So this concludes the data modeling part. Any questions? Yeah. 42 slides. Oh, I need to go back? This one? No.
Okay, so do we have to account for the order in the name column, for example?
The order of the columns, no, but the order of the rows, yes.
Of the values.
Of the values, yes. The order of the rows is important because they are arrays in JSON. It's an array of string.
Yeah, but we could say last, first, and Albert Einstein. I mean, so these are the same, like the JSON definition here, they are same, right? But so this one accounts for the order and the other one with arrays.
So here it's the order of the objects.
It accounts for the order of the name and type, but this one, I think.
I see. No, name and type don't have any order because they are keys. In objects, you don't have any order.
Set the string value. It can be
in here.
Yeah.
Yep.
It can have name item. First, last, or last, first. Like,
so, oh no, you would. It has to be the way it's displayed. It's first and then last, and Albert and then Einstein. Yeah. It's just a visual, but the way you see that the order matters is because it's an array. That's how you know, right? When you have an array, the order matters. Okay. All right. It's perfect because we have enough time to start MapReduce with a little surprise that I have for you. So let me stop the recording here.